Today's first day of probability, and randomness is really important. If you don't do things randomly, then probability is not something that would be involved. Probability is calculated when things are done randomly. So if I throw a pen to somebody, I'm not randomly throwing it to them. I'm choosing to throw it to them. But if I randomly select their name out of a hat where I can't see the names on the cards and I grab one, that is random. Okay? So the official is that no individual outcome is predictable, as in I can't predict if I had all of your names in a hat who I'm going to draw, but I can say things about generally, since there's about 25 of you in the room right now, that there'd be a 1 in 25 chance that I'd get you. So I can kind of talk about long range patterns. Also, if I'm flipping a coin, do you get I can't predict if it's heads or tails, but I can predict in the long run it's going to be about half and half. Okay. So next thing, an event is a thing, like you're flipping a coin. You're throwing your pen to somebody. Whatever the thing is, the event is something that's happening, and it'll have outcomes, like only certain things can happen. Like for instance, if you roll a die, something's going to happen. You're going to get a 1, 2, 3, 4, 5, or 6. And that is the outcome of the event. The sample space, this is important because a lot of people don't know this one. You probably knew the other ones, but sample space is all the possible things that can happen. So if I'm rolling the die, there's 6 things in the sample space. Okay, it's a fancy name to say all the things that could happen. All right, so next one is probability, is the measure of the likelihood that an event will occur. So obviously probability is involved even in, we just lost Prince recently, and life insurance companies their job is to kind of predict how long you are going to live. It seems kind of crazy, but it's true. When you get a life insurance policy, if they give you a really low rate for your life insurance policy, then that means there's a very low chance that you're going to die. Okay? And if life insurance companies will check your blood too when you do life insurance with them. Do you know what they're looking for? Cancer would be one of the things. Yeah, I don't know if you can get blood pressure from blood. But you can get like blood sugar, yep, see if the person is like diabetic. You can see if they have like a blood's really got a lot of fat in it, for instance, and that maybe implies cholesterol, maybe implies that they're going to die early from heart issues or whatever. So there's ways they can predict your life expectancy. I'll give you an example for my father. I checked when he was really old. We actually were looking into life insurance for him because of a complicated financial planning situation. He had money in an IRA that he thought maybe I could take all the money in that IRA and buy a life insurance policy with it, even though we know it's going to be really expensive, because then the life insurance proceeds won't have any tax on it. So there's a reason why we were checking. But I did the quote for my dad, and it was the only kind of life insurance they'll do at that point is where you pay all the premium up front because he's already really old. So you have to pay him all the premium up front, and then when you die, they'll give you the payout. Okay, his premium to get $1 million of life insurance would have been to pay about $990,000, and then they would give him $1 million when he died. Well, that should have given us a sign, because within 1 year he was dead. So anyway, he was pretty healthy when we did the quote for him. But the insurance companies looked at everything. They know charts, they know probabilities, they know what he had for past history, and they were able to predict with pretty good accuracy that he was going to die soon, and he did. Do they tell you that? Yeah, they tell you. They basically are saying, although no insurance company wants to say you're going to die on next year on Tuesday in June and the third Tuesday or whatever. They don't want to tell you that. That's pretty grim, but that's kind of what they're calculating. They're giving their best guess so they can set the rates then. On the other hand, for somebody who's young, like you guys are really young, buying life insurance for you is really cheap because the probabilities of you dying are very low. It still happens, but it's extremely low probability. Okay, so if there's a no chance, well, for life insurance, there's no zero probability. Everybody, in fact, is going to die. In fact, if you're going to say probability you're going to die, you will, just given enough time. There are guys in Silicon Valley right now who have a ton of money and don't want to die. And so they are working on ways to live way longer. Some of them are predicting that they are going to be able to double the normal lifespan. They are thinking they might make it to 160 years old. And now, if you're picturing like a super old guy living to be super old, that's not what they're picturing. They're picturing being able to live totally healthy, like think about an active older grandpa that still can do everything, all the way until they die, like active and healthy life. Because if they figure this out, that isn't like for living forever. Of course, that's been the quest ever since people were coming to the Americas trying to find, what it was called? The Fountain of Youth, yes. They're not trying for that, which would actually make you live forever. They're trying to, though, find ways to just extend life much longer than it currently is lived. If they figure that out, that'll really change life insurance, for instance. They can make it way cheaper, but depends on the person, too. If you're going to actually do these things that would cause the long life. So anyway, so certain to occur, death is one of those things. And sun rising in the morning, although is it really certain the sun's going to rise in the morning? Well, you could go, is there a chance it'll blow up between now and tomorrow morning? Not really. No chance? Well, it would round to zero, I'll give you that, but I think isn't there a tiny probability that the sun will blow up between now and tomorrow morning? All right, I know, extremely low. So that goes way down here. But do you get how there's very few things that are certain to happen? And there's very few things that are certain not to happen. You might say, well, we're not going to have a giant earthquake in Minnesota, but we live on a fault line. If you don't know that, it's true. But is it an active fault line? No, but that doesn't mean it couldn't start activating tomorrow, and all of a sudden there could be a giant earthquake here in Minnesota today. If it starts right now, you guys will be really impressed. So anyway, the probabilities that you're thinking of here always go between 0 and 1, and 1 means certain, and they're really rare. 0 means certain to not happen, also really rare. A lot of things in the middle. Okay, so let's go to this. This is a table, and it's a really important one. It's got all the things that can happen when you roll 2 dice. And I kind of don't like it in a way because it's kind of giving away some of the things that we used to like make you figure out. But it is one of the most important concepts in probability is 2 dice. Because it totally changes things when you have 2 dice. When you roll 1 dice, they're all equally probable. When you roll 2 dice, they're not. Can you see which one seems to come up the most? 7. Why? Is it because 7s are lucky? No, because there's a lot of ways you can get a 7. 6 and a 1, 6 and a 1. Why did they do it differently? Because they're different colors being the 6. The first die being a 1 and the second die being a 1 is different. 2 and a 5, 5 and a 2. 4 and a 3, 3 and a 4. And that's 6 different things that'll give you a 7. Whereas what's really rare to roll when you're rolling 2 dice? You ever heard of snake eyes? Okay, that's really rare. And just equally rare is boxcars. That's what that's their name is. 2 6s. All right. So you can bet on this in Las Vegas. You can walk up and say, I want to put a bet on rolling snake eyes. And they'll have a huge payout if the person rolling, which can be you if you're betting, or you can bet on somebody else who's rolling and say, I think he's going to roll snake eyes next. What's the probability you actually roll snake eyes? 1 in 36. So if you bet $1, do they give you 36? No, that would be if it was exactly fair. If you bet $1, they might only give you $30 back. If it was exactly fair, then if you bet $1, they should give you 36 back. But the game is not set to be fair. Casinos are not doing this to make it fun and fair for you. They want to make a little advantage for themselves. So they'll only pay you 30 if it actually pays out, or something like that. All right, so you can bet on these probabilities in Las Vegas. In Minnesota and certain places you can, but it's not standard throughout the whole state. So anyway, probabilities obviously can be involved with casinos. And we'll talk more about that later. So next thing, experimental versus, oh, wait a minute. In the context of sample space, What is the sample space? All the things that can happen. So there are 36 things in the sample space. That's all of these things. That could happen, or 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 that. Do you get what I mean? All of those things together is the sample space. Those are all the 36 things that could happen. All right. Experimental probability is where you are actually doing an experiment and then you figure out what happens. Like, you would expect this die to probably come up 1 out of 6 times. It'll come up a 6 or a 2 or any of the things on it. But what if I actually roll it a whole bunch of times and it keeps on coming up 6 way too often? Could it be a weighted die? Yes. So by doing an experiment, you might find out that you were expecting the chances of a 6 to only be 1 in 6. But what if it keeps on coming up like every other time? Then those are weighted dice. And there is a way to, it came up. If you weight the dice, you can not guarantee a 6, but you can increase the probability of the 6 by basically putting a heavy weight on the bottom side of the, inside the die, so that when it lands, it tends to want to flop over to that heavy side being down. So, but it's still, again, it's not a lock, but it's a more likely that it's going to. All right. So then there's a theoretical probability, and that's not actually doing an experiment. That's just saying, okay, it's a die. It looks like it has 6 sides that are equally likely. So what's theoretically the probabilities? 1 in 6. And that's doing it based on just head knowledge, as opposed to experimental, where you actually do an experiment, count how many times it actually happens. How about a coin? Flip a coin a bunch of times. What if I have a coin and I do it 1,000 times, and 75% of the times it comes up heads? Are you suspicious of the coin? If I did it 1,000 times, don't you think by then I've got a pretty good idea that the coin is messed with? It's weighted. It's true. If I had only flipped it 4 times, and 3 out of 4 times it came up heads, now are you suspicious or not? 3 out of 4 times, it's only 4 times, right? But if I do it 1,000 times, and 75% of the time it's coming up heads, that's a reason to be suspicious. You've done what's called the law of large numbers. The law of large numbers is basically that if you keep doing it, you're going to eventually get to the theoretical probability. All right. So, contingency tables. This is just a table of facts, and this is just like a survey kind of a deal. This is awesome. Do you remember seeing that in Simpsons? And Flanders had the leftorium. Basically, it'd sell things that were made for left-handed people. Anyway, so we got right-handed and left-handed people. And in this little poll, there was 87 people who were right-handed and 13 who were left-handed out of a total of 100. So what the heck are all those other numbers? They're broken down based on male and female. By this survey, do you see that if you are left-handed, it is more likely you would be male? All right, so then to answer questions about this, the probabilities, it's usually out of 100, but can I change the question so it's out of something else? Yeah, if I just want to ask about males, out of the males, as soon as I do that, do you get the whole rest of the chart disappears? If I say out of the males, blah, 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 well then it's out of what? 52. See what I mean? You can narrow it down this way. Drill down, sometimes they say about data, on one of the groups. So let's say I'm talking about, given I'm only talking about the left-handed people, do you get all of this part of the chart just disappears and the totals disappear too? If I say given I'm just talking about lefties, what's the probability it's a male? If I pick from all the left-handed people, what's the probability it's a male? Would you write down what you think the answer to that is? It's a fraction. What did you think? That is correct. Because this is the total, and the total always goes on the bottom. And I like to, this is a thing about probability I'm going to say 8 million times. Probability is what you want over what things were possible. There were 13 possible people I could have picked, and I wanted the probability of male. So 9 out of 13. It's what I wanted, not necessarily that I want it to be a male, but I want to look into probability of a male out of what was possible. Want over possible. Okay? That's going to come back when problems get really hard. I'm often going to refer back to that. What you want goes on top, and what's possible goes on the bottom. All right, so this is some super basic questions, but let's get to 3. What was the probability that a person pulled was left-handed? Did they say consider only the left-handed people, or were they talking about the whole poll? And therefore, is this out of 13 or is this out of 100? It's out of 100. Okay, then that's what was possible. Do you get what it's out of is what's possible, and that goes on the bottom. And then what is the thing that we wanted to look into? Left-handers, which is how many? 13. If I just pick 9, do you get I'm leaving out the female lefties? So I have to go with 9 and 4 together, which makes 13. So 13 out of 100. What's the probability the person pulled was female? Did it say now? This is a new question. Did it say anything about left-handed? No. So then it's just females out of total. Again, it wasn't narrowed down to right-handed females or left-handed females. It was just about the totals. So it's out of 100. And then what was what we wanted to look into? So therefore, 48. Out of what was possible? All 100 people were possible. 48 out of 100. Should you reduce? Yes. Should you get a decimal? Technically, yes. But this one's really easy because it's out of 100, so it's just point what? 0.48. Yes. Good question. I generally like fractions because they're easy with numbers, but if they're out of 100, it's really easy. Just make them a decimal because technically probabilities are supposed to be decimals. This is still, even if I reduce it down to something really simple like 4 out of 5, that's still supposed to be changed to a decimal. It's just the easiest fraction I can make besides making it a decimal. So 4/5, I could change it to a decimal as 0.8. Better to say the decimal. The decimal is the best, but oftentimes on your homework, I'm okay with just leaving a fraction because it's kind of busy work to have to take the numbers, put them in a calculator, and divide them. That's all you do is divide them. So if your answers are going to come out to 23 out of 497, I'm often going to say it's okay to leave it like that because I know what you'd do, and you know what you'd do. 23 divided by 497. You get the decimal. I will say that the decimals are easiest to read because if you say that, you know right away it's 80% chance, you know it's a high chance. This looks like a low chance, but it's hard for me to know how low of a chance is it. If I change it to 1%, I'd be like, oh, I know what 1% means. That's really, really low. All right. And that one, by the way, would be less than 1%. So that'd be a really, really low chance. Okay, moving on. Go to this one, the number 5. What's the probability of randomly chosen male? Ooh, that's different. Do you get how they just meant it's impossible to pick anyone else than males? A randomly chosen male is basically narrowing it down to only males should be considered. So do you get all the rest of the chart is irrelevant for this problem? That's an important thing to do. You got to be able to narrow it down like that. Here's another way to say it. Given he was a male, then it's only that. You had to pick from those. Then what's the probability they're right-handed? 43 out of 52. So as soon as you get the idea that contingency charts really just are about narrowing it down to what you want, maybe they only say, we're only talking about lefties here. Given we're only going to pick from lefties, right there's all I need. That and that are gone. Then you only have 3 numbers left, and it's really easy. Okay, so try to figure out how to narrow it down. So this last one's the hardest one, bolded in. What is the probability that a person is left-handed given the person is female? Ooh, right away, given the person is female, do it yourself. Limit it down to only one set of people and then figure out what you want over what's possible. You may write this as a fraction. As soon as it's given they're female, that's the only thing I need. The rest of it goes away. Do you get that it's either 44 out of 48 or 4 out of 48? And now what do I actually want? Probability that they are left-handed. That's these. That's what I want out of what was possible. That's 4 out of 48. Raise your hand if you had that one right. Okay, good. All right, so one last slide for today. I'm going to pause for a second. Okay, so I've got it now. Here's your last question. We are going to actually take a little poll here and show you how you can get this data. So if you haven't heard these three Prince songs, if you haven't heard any of them, you can pick any one you want, go based on your favorite title of the song, okay? But he had three songs that we're considering here: Little Red Corvette, Purple Rain, and 1999. That was the one who was like, tonight we're gonna party like it's 1999. Anyway, I was around back then. Were you guys even born back then?
1999, I was born in 2000.
Some of you were born in 2000. So some of you weren't even born when that song. All right. All right, so here's my question. Little Red Corvette, if you are a 9th grader, and by the way, if you're an 11th grader, I apologize, you're going to go in with the 10th graders, but if you are a 9th grader and you would pick out of these three songs, Little Red Corvette, raise your hand. You only get to vote once. All right. If you are a 9th grader who likes Purple Rain, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you're a 9th grader who would like 1999, raise your hand. 1, 2. If you're a sophomore who would like Little Red Corvette, would be your favorite of the three songs. 0. Who's a 10th grader who likes Purple Rain as their favorite song? 1, 2, 3, 4, 5, 6. And 1999, 10th grader. 1, 2, 3, 4. Did somebody vote twice? Okay. All right. And then totals. From here, you guys can do this really easy. Just what's this one add up to? This one? 15. This one? And then totals across this way. 9 plus 1 plus 2, 12, 10, and then the total, 22. And that does add up this, and this, or this and this, all add up to 22. Neat. Okay, now, I'm going to ask you a question about it. Number one, what's the probability that a randomly chosen 10th grader, notice, it narrows it to only 10th graders get picked here. A randomly chosen 10th grader prefers Little Red Corvette. What was the probability of that? 0, because it's 0 out of, technically anything would be 0, but 0 out of what? 10, because we were only considering 10th graders. All right, so 0%. And that is a real answer in this case. It's rare, but it's true in this case. What's the probability that a randomly chosen person, I could pick from any of you, prefers Little Red Corvette? Oh, wait a minute. No, here it is. Probability that a randomly chosen person who prefers Little Red Corvette is a 9th grader. Now, do you get it narrowed it down to only people who liked, no, only 9th graders. No, I'm wrong. Only people who like Little Red Corvette are chosen from. That narrowed the chart down to only this. And now it's what? 1 out of 1, which is 100%. Remember me saying it's really rare to get that? Well, you guys just proved me wrong. Given a person prefers Purple Rain, what's the probability they are a 9th grader? As soon as they said given, you know you narrow it down. You're narrowing it down to only the Purple Rain people, and therefore, not that, but that. So your numbers better be from there. And therefore, what's the answer? 9 out of 15, which does reduce. 2, I can factor that. 3 times 3 over 3 times 5 cancels. 3/5. Also known as what decimal? 60%, 0.6. No. Hey. Focus. Almost done here, but can't be turning around backwards when I'm talking. Okay, so that's probability or contingency tables and probabilities and a whole bunch of like opening terms and how you set up your probabilities. Your homework for today is from the worksheet. I'm going to pause for a second while we pull that up. Okay, it is 15.1, lesson 1, and this first problem, part A with A, B, C, and D are all very good, reasonable questions. Remember to narrow the chart down when they say given that it's a woman, like a randomly chosen woman, that limits it to only women. And you got to narrow the chart down to only include women, for example. All right, so be careful of those. And it's always what you want to consider over what was possible. And what was possible in that case was be all the women, and so out of that. All right, And in this one, it'll say, listening still, round to 3 decimal places. That means using a calculator and getting the decimal. So I am going to ask that you do that for today to get the decimals, because my answer key is all going to be in decimals. Okay, so it's not that hard to divide 2 numbers to get your final answer. All right, moving on. Problem number 2, all of those are very reasonable. And problem number 3, marbles problems are like something we do all the time. So I think we're going to skip, let's see, 4, we talked about that so much we can skip that. 4, we can skip 4, all of problem 4. Then I would like you to figure out some probabilities. In the notes, we had a slide that would show you this answer. What's the probability you're going to get a 2? Remember how many ways there were to get a 2? There's only one way to get it, so it's 1 out of 36, right? Okay, why is there 3 ways to get a 4? Because a 2 and a 2, or a 1 and a 3, or a 3 and a 1. Oh, okay. All right. Try to focus on the one that I just told you which one we're going to be doing here. So you do not have to fill out this chart. You can reference that in your notes if you'd like to, and you can just answer this very last question on the page. Okay. So told you a couple you could skip there, and again, the only one was here to skip 4A and B, and then the top part of 4 here, the other 4. I get how there's 2 4s and that's confusing, but okay, that's all I have for you for today.